This presentation is part of the TI-Nfocus AP Calculus video series. In this video, I'll discuss some technology solutions and problem extensions for the 2019 AP Calculus exam, free response question AB4 BC4. My name is Steve Kokoska. I'm a professor at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Here is an outline of the information presented in this video. I'll start by reviewing the free response question, and then the scoring guidelines used at the AP Calculus reading in Kansas City. And I'll highlight the solutions presented in these guidelines, not how the points were awarded. I will present the solution to each problem in a little greater detail than given in the scoring guidelines. And even though this was not a calculator active question, I'll show you how to use technology to explore and answer parts of this question, and to confirm solutions where appropriate. And because the free response questions are usually very comprehensive, I will suggest some problem extensions, additional AP Calculus type questions, some of these associated with the information given in the problem, and some of these may be calculator active. This free response question involves a cylindrical barrel with diameter 2 feet, collecting rainwater, and we're told that the water also drains out of the barrel at the bottom. The rate of change of the height h of the water in the barrel with respect to time is given, and we are reminded of the volume of a cylinder with radius r and height h. In Part A, we need to find the rate of change of the volume of water in the barrel with respect to time when the height of the water is 4 feet. In Part B, we need to determine whether the rate of change of height of the water with respect to time is increasing or decreasing when the height of the water is 3 feet. And in Part C, we're given an initial condition, and we need to solve a differential equation for h in terms of t. Part A was worth 2 points. The first point was for finding an expression for dV dt, for understanding that this is a related rates question, for taking the derivative of both sides of the expression for volume with respect to t. The second point was for using the given expression for dH dt to produce an answer with the correct units. Part B was worth 3 points. The first point was essentially a power rule point, for finding the derivative of minus 1/10 times the square root of h with respect to h. The second point was a chain rule point. That is, when finding d squared h over dt squared, we need to multiply by the derivative of h with respect to t. And the third point was for the correct answer with a suitable explanation. Part C was worth 4 points. The first point was for separating the variables, bluntly, for putting all the h's on one side and all the t's on the other. And it doesn't really matter where the constants go. Looking ahead, we simply try to place the constant on the side that leads to the easiest algebra. The second point was earned for 2 correct antiderivatives. That is, the student must integrate on both sides of the equality with respect to the correct variable. The third point was for including a constant of integration in a correct manner and for using the initial condition, simply using the values for t and h. And finally, the fourth point was for producing the correct explicit expression for h of t. Let's take a closer look at the solutions and use technology to help confirm our results. In Part A, we need to find the rate of change of the volume of water in the barrel with respect to time when the height of the water is 4 feet. Now, translated into mathematics, that means we need to find the value of dV dt when h is equal to 4. Now, I think the most efficient way to solve this problem is to start with the expression for the volume of a cylinder with radius r and height h. We know that the radius is a constant, 1. Be careful, the diameter is 2, but the radius is 1 here. So in this problem, the formula for the volume is simply pi times h. This is a related rates problem. Both the functions v and h are really functions of time t. So take the derivative of both sides with respect to t. On the left, we get simply dv dt. On the right, the derivative of h is 1, and using the chain rule, we multiply by the derivative of h with respect to t. And we're given an expression for dh dt. Now, all we have to do is evaluate dv dt at h equals 4. So the volume is changing at a rate of minus pi divided by 5 cubic feet per second. Now there is another, perhaps more general way to start this problem, and that is by differentiating both sides of the expression for volume with respect to t. We consider both r and h as functions of t. We need to use the product rule and the chain rule. Now this expression simplifies because r is equal to 1, and since the radius is not changing, dr dt is equal to 0. And even though it might be too much of a good thing, we can use technology to explore and confirm this solution. Here is a way to do this using the TI-Nspire. First, I defined a function v, where r is a variable and h is a function of t. Next, I found the derivative of v with respect to t, and we get the exact symbolic answer, which is cool. And then using the vertical bar, which stands for, in my mind, such that, I evaluated the expression for dv dt for, or such that, r is equal to 1 and h is equal to 4. And the calculator returned the exact symbolic answer. To answer part B, we need to find the derivative of dh dt. So we take the derivative of both sides with respect to t. And remember that h is a function of t. On the left, we get d squared h over dt squared. On the right, minus 1/10 is a constant. Take the derivative of the square root of h, or h to the 1/2, using the power rule, and then use the chain rule. Multiply by the derivative of h with respect to t. Here, I did a little simplification, and I used the expression for dh dt. And finally, just a little more simplification. So it turns out that d squared h over dt squared is constant, 1 divided by 200. Since the derivative of dh dt is positive for all h greater than 0, the rate of change of the height is increasing when the height is 3. And here's a technology solution. Perhaps a little excessive and clumsy, but at least here's a way to confirm my result. I defined a new function, h prime. In the context of this question, this is dh dt. I found the derivative of h prime with respect to t. And finally, I used the expression for dh dt given in the problem. I feel pretty confident in my answer, 1 divided by 200. Here is a related example for you to consider. In the context of this free response question and the cylindrical barrel, suppose the rate of change of the height h of the water in the barrel with respect to time t is modeled by this expression. This is a little different from the original. When the height of the water is 4 feet, is the rate of change of the height of the water with respect to time increasing or decreasing? And don't forget to justify your answer. In part C, we need to solve a differential equation. Well, really an initial value problem, using the method of separation of variables. So, first we separate the variables. Put all the expressions involving h on one side and all the expressions involving t on the other. Now the constants can go on either side, so we try to look ahead and place the constant on the side that will lead to the easiest algebra. Integrate both sides of this expression, on the left with respect to h, on the right with respect to t. On the left, I use the power rule for integrals, or some call this the backward power rule. And on the right, the antiderivative is the constant times the variable t. Now I included one constant c on the right, which can be thought of as the sum of two constants associated with each integral. Next, I used the initial condition, so I let t equal 0 and h equal 5, and I solved for c. Use this value of c in the expression relating h and t. And then finally, find an explicit expression for h in terms of t. Here is a technology solution for part C. The TI-Nspire has a built-in function to solve differential equations, called DE-solve. The arguments here are the differential equation and the initial condition, the independent variable, here t, and the dependent variable, here h. I'm not sure of the algorithm used to solve this DE, but notice that my answer is stated in terms of the square root of h. Now I need an explicit expression for h, so I used the solve function. The answer perhaps provides some insight into the DE-solve result related to the domain. And here's another example, an extension of this free response question that uses this differential equation. Sketch the slope field for this differential equation, and then on this slope field, sketch the solution curve that passes through the point 0, 5. And finally, here's one more example. And the solution here involves some work that some students mistakenly presented in this free response question. Suppose a water tank is in the shape of an inverted circular cone. The base radius is 3 meters and the height is 9 meters. Water is being pumped into the tank at a rate of 5/2 cubic meters per minute. Find the rate at which the water level is rising when the water is 4 meters deep. I hope this video gives you a better idea of how to solve this free response question. Some good ideas for additional practice AP Calculus exam type questions, how to use technology to solve some of the parts of this problem, and to explore, confirm, and visualize results. This problem presents some good opportunities to discuss related rates problems and separable differential equations. And just a reminder, there are lots of valuable resources on the TI website. There is material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.